Okay, good afternoon, everyone, and welcome to the second lecture of this semester's Kent Seminar series. As you all know, the theme for this semester is autonomy in transportation, and today we're very delighted to have Professor Ziran Wang as our speaker. Professor Wang is an assistant professor at Purdue University's Lyle School of Civil and Construction Engineering. He is also the assistant director of the Institute for Control, Optimization, and Networks. His research focuses on digital twins, autonomous driving, intelligent transportation systems, and human autonomy teaming. He earned a doctorate in mechanical engineering from the University of California, Riverside in 2019. Everyone, please join me in welcoming Professor Wang.
Well, thank you very much for the introduction, and it's a great pleasure to be here. Thank you everyone for coming, and for those of you who are celebrating, Happy Chinese New Year. It's really a good way to celebrate this for myself to come to give a talk here at University of Illinois. So again, I'm a assistant professor at Purdue. I joined Purdue 2022, and before that, I actually spent 4 years working for Toyota as a principal researcher based in Silicon Valley. And I have done research in this wide domain of, we call it connected automated vehicle or autonomous driving. Especially we're looking into how human can collaborate with those vehicles. So that's why, human autonomy teaming is another research focus of my research. Thank you. So, going back to the background that I started all those research, and this is actually from my, Toyota years, where we look into the personalization of all those different features. So, not sure how many of you have used the feature called adaptive cruise control on your vehicle. And you all know that if you turn that on, basically the radar on your vehicle will keep tracking the front vehicle. I happened to switch it to a Volkswagen vehicle because I gave this talk at Volkswagen last month, where the vehicle will follow the preceding vehicle at a certain distance and at a certain speed. And the trick that you can play with this system, and you always have a setting like this on your steering wheel, is you can change the car following gap. And for those of you who are traffic engineer, you know it's by time. It's called time gap, and the gap can be, say, the longest gap is, say, 3 seconds. The second longest, 2.5, then 2 seconds, and probably 1 second. There might be 4 settings, sometimes 3 settings, by changing the buttons, right? So the story is we actually heard a lot of complaints from our Toyota and Lexus customers through the dealership that they complain this is not automatic. I mean, they say, you claim this advanced driver assistance system or automated vehicle, but why do I still have to change the settings all the time? Including myself, I drove my vehicle here from Indianapolis yesterday. The 2-hour trip, I thought I probably changed the settings like 20 times during the whole trip. Sometimes you want to follow a little bit closer to the preceding vehicle to avoid other vehicles cut in. Sometimes you want to follow a little bit further. Probably it's starting to rain. You don't have that good visibility. And if you look at the survey that we did, so basically, many people, they change the settings during a single trip. And how often? And many of them, they change like multiple times. Why? Because those different reasons, right? Traffic condition change from time to time. Weather can change from time to time. Personal mood, when you drive from your home to work versus you drive from work to home, you have different preferences for the car falling gap and everything for the such a system. So we were thinking whether we can make this system personalized, whether we can directly learn from this human's interaction with the vehicle, by either changing the buttons and everything, and then make this system more intelligent. So that was really the beginning of all those work that I have done in this field. We want to make an autonomous system that's more personalized, that understand the needs from the human beings more. We don't struck into scenarios like this. This is a video that I shot. I have to change the settings from time to time. I was pressing the button, so it was 4 bar, which means I followed that preceding vehicle at the furthest place, and sometimes 3 bars means a little bit closer, 2 bars closer, and 1 bar is closest. So whether we can make it personalized to understand everything. And why we need this, it's not just for Toyota vehicles, it's not just for Lexus vehicles, it's for all those different vehicles, even for Tesla. If there are Tesla drivers out there, yes, it's a cool feature. It's they call it FSD, which is not full self-driving, but still it's a very cool feature, right? But I think we look up at the forum. Some people they complain that how aggressive this system is, their FSD is, while some other people complain how conservative it is. Exact same system, and they have all different opinions on the system. So the key argument is still how we can better understand humans' interaction with such an autonomous system, and make it more personalized, make it more satisfy their needs. So that's really the onset of our research. We call it human autonomy teaming or human AI teaming. And we have really looked into all different levels of the research, starting from looking at vehicle dynamics, looking at vehicles change of speed, acceleration by the driver, pushing on the paddles and probably steering wheel. And then we transition into looking at the in-cabin monitoring data. Like if you're driving a Tesla vehicle, you have a camera looking at you all the time, right? So we want to learn from people's gesture, head pose, emotion, everything, try to learn the underlying needs for such a driver and sometimes passenger on the vehicle, whether they're happy about it, whether they're angry, whether they are relaxed and everything, and how we can tune that system a little bit. Now, this is ongoing work where we want to also look at whether we can model this specific human's physical states by using some wearable devices, eye tracking glasses, heart rate by using a smartwatch, ECG, EEG, and things like that. And the focus of today's talk is actually the last part. And we found this might be the most intuitive, direct way that autonomous system can understand the human, which is through audio signal, right? Which is directly through verbal command. Whatever you want our system is to be, just say it. Just say it aloud, and we will try to understand you. So you see all those different four levels of work. We have publications, and it's really the past 2 years, we transition into this, and our students look into this a lot. We publish a lot of papers on all those top AI conferences. And why we need this? Because traditional system that we figured out on our vehicles, and even for just a regular system, like even the Siri that we are using right now, I think it's still kind of not smart enough compared to the large language models. So taking this as an example, these two drivers saying the exact same words, or those can be just riders, passengers on an autonomous vehicle, right? The rush hour is approaching. So this driver or this rider might mean you need to be as quick as possible to avoid the traffic. While the other one might mean that you need to be careful as the traffic will be complex, right? One is a more aggressive passenger, one is a more conservative passenger. But they are saying the same words, they are meaning the exact opposite thing. And traditional system, if you're just saying this thing, you're just describing this, the system cannot comprehend what you really mean, the underlying needs of yourself, right? You have to be very specific. And that's why how large language model kicks in. And we have actually benchmarked all those different models out there. I have some of their logos right here. I added this yesterday just because many of you know. We are still trying to look into this. I talked to my students last week, actually not last week, but 2 days ago, and we are going to benchmark DeepSeek as well. But we have done all those others and a few others that we didn't include. But the way that we did it is, of course, all the strengths of LMs, right? I talk about how we need to understand humans more. Even if it's a full self-driving vehicle, there's still a human passenger on the vehicle, right? You still have preferences, whether you want this vehicle to be more conservative, aggressive, whether you want to stop by a grocery grocery station, a gas station, a grocery shop, or something like that. But really, how we use LM in our research, we are running them as an add-on feature to the existing AV stack. By AV stack, I mean perception module, planning module, control module. We are not replacing any of them. We're not doing any so-called end-to-end approach so far, but we use them as an add-on. And we're now replacing, as I said, for the fear of hallucination. For those of you who know or who use ChatGPT nowadays, hallucinate a lot, right? And safety hazards, also you are not able to get timely response from the system. And all those are bear in mind while we are deploying this. And we can always kick out such a system. For instance, the research I will show later, we use large language models for planning, but we just use them to further fine-tune our planning algorithms instead of replacing our planning module. So that's the way that we use it, and I will show you more details. So the high-level thing is we utilize large language models as humans' brains to provide high-level guidance for autonomous vehicles. So I will actually talk about 3 different pillars of the research, and due to a time limit, probably for the first one, I'll quickly go through that. But basically, we have developed the first, open data set, benchmark data set for large language model for autonomous driving. And this work was published on CVPR last year in June, and we submitted like September, October timeframe of 2023. So it has been more than 15 months or so. But the motivation is, there are limitations for LLM-based agents in autonomous driving, how to evaluate this and that, and there are safety concerns. So that's why we think, having a open benchmark data set will be valuable. So we use this thing called highway environment data set. It's an open data set. And we further annotate a lot of different scenarios, around 5,000 scenarios as the instruction sim pairs. So you have distance related, speed related, pulling over, routing, lane change, overtaking, and stuff like that. And also highway scenario, intersection scenario. And we make it an interactive environment and covers all those different random traffic scenarios. And the key thing about this is we made it available for you to test out whatever algorithm that you have based on this scenario pairs. With the data set, you can initialize it and build a simulation based on all those different scenarios, have your command running on that. We also have the API for that. So I won't go through all those details. You can always find the details on our paper, which is not really the focus of today's talk, but I just wanted to tell you that benchmark data set like this, and there are a few after our work are there for you to start to do research in this field. But I do want to mention a little bit more during today's talk is our real world experiment. As I introduced at the very beginning, I work in the industry for 4 years. So a lot of my research is always application driven. And I always first think about what's the end product of this research, whether we can really deploy this in the real world, on a real car, and affect the way that we travel. So that's why this research is directly about real world experiment, and we want to use large language models to help the decision-making process for autonomous vehicle. Specifically, we want to provide a personalized driving experience, a continuously personalized driving experience for human users. The traditional system, they don't really have a verbal command interface like the systems that we have, even for Tesla vehicles. They don't have a very advanced communication system besides just pressing the screens. And we think developing a common understanding system that can understand all these complex and implicit commands from the human drivers and passengers would be very beneficial. So our system is called Talk to Drive, and we really develop a personalized driving system on a real vehicle. So this is our test vehicle. That's actually my personal vehicle used as a surrounding vehicle. So this vehicle will do several things based on what the human passenger described, which I will show in our demo. So this is a busy diagram, but which showcases how our Talk to Drive system works. As introduced at the very beginning, I will also work on the domain called digital twin. So a lot of my stuff is always divided into these 2 different worlds. So there's always this physical side, and there's always this digital side or cloud side. We deploy the thing on the cloud side. So you can consider this is a physical system, this is a digital twin of the system, which you have all those different replicas of the data in the digital space. But if we kick this whole thing out, cloud side out, if we kick this left side out, this core piece right here is just a traditional autonomous vehicle stack. You have your perception, you have your planning, you have your control, and perception is connected with your sensors. You have your CAN bus to actuate your system for control, for steering, for braking and acceleration. That's a traditional system. And as I introduced at the very beginning, we just add on this whole large language model framework to run in parallel with our existing AV stack. And the way it works is, okay, we have a human that can provide feedback and guidance to the system. And the feedback will then send to a speech recognition system on the cloud, which convert the verbal command into a text command, right? Because large language model, it takes in text command. And that speech recognition, we use a thing called Whisper API. It's a open source API that can convert the verbal command into a text command. And the text command will be then sent to the large language model. In this case, we benchmark all those different models. And the feedback will be sent as a code. It's not just a simple command, it's actually a code, and we use the so-called code as policy to then send back to the planning module to actuate. And we also have all this context information. You have the weather information, the traffic law document, so the speed limit and everything, and the traffic environment information also sent as a context for the large language models. What's more is we also have a memory module, so it logs all those historical interaction between yourself and the large language model, so they will be also considered when they make reasoning. And I'll show you what are the scenarios that we talk about. So basic stuff are there. We use chain of thought prompting. We use in-context learning, and we use code as policy to generate codes for the planning module to consume. And the memory module is really key. So this is how it works from a high level. This block diagram. So you will switch on the system by saying a word's command. It's like, say, hey, Alexa, or hey, Siri. And then the system will be switched on. You will enter your command, say your command, and then the context information will be also retrieved from the cloud. The system message will also be retrieved. System message is your vehicle current speed, status, what gear you are in, and things like that, and then sent to the large language model. Large language model then will be generating this program as code for your vehicle to actuate through ECU, and that's it. That's how simple it is. And this green part is a feedback loop, right? We can also provide feedback as human beings to the system, switch on the system by saying evaluate, switch that on again, providing your feedback, I was happy about what you did, or, you should still be more aggressive, or things like that. Send to the memory module over there, and then the historical data will be concatenated to your real-time data next time. So say the trip 10, you say something, and besides the words that you say during this time, all those past 9 trips, all those information, the interactions between you and the large language model will be concatenated with the new data. So they will be sent to the large language model in bulk for the reasoning process. So that's about how this system works. It's theoretically very simple, but let's see how it works on our vehicle. So this is our testing vehicle. And it's similar to, I just talked with Professor Alireza, the vehicles that he has. It's a drive-by-wire feature enabled. We have the LiDAR, radar cameras and everything. We have this ECU on the vehicle, the computer that can do sound processing. These are scenarios. As I said, we tend to think about what kind of scenarios that can really showcase the value of such a system first before we actually develop all the systems. So these are scenarios that we think out that can really show the value of it. The parking lot scenario is at the North, we call it North Stadium parking lot at the Rose Stadium. So it's a Purdue University's football stadium where we have a giant parking lot. And we are telling the story that you are going to a football game, you want the vehicle to drop you off, but the vehicle needs to decide which is the parking space to park. The intersection scenario is an unprotected left turn. As many of you know, that's a very risky scenario. So our vehicle needs to do unprotected left turn, and there's going to be another vehicle crossing from the other side, going straight. The highway scenario is a 3-lane highway where there's aggressive driver in front of us and doing like aggressive behavior, anomalous behavior, and we have to make decisions what to proceed. So those experiments were conducted. This is at Purdue campus. Those two is at a abandoned airport runway, similar to this one that you have right here in Columbus, Indiana. And the objective is really to verify combined understanding ability and showcasing how they can make decisions. And in this case, it's just large language model. There's no vision piece back then. And then validate personalization capacity. And in the demo, we actually will showcase 2 scenarios or 2 trips per scenario. One is before the human provided feedback, and the other one is after the human provided feedback, how this system gets further improved. So I'm gonna play this video to showcase this demo. It was conducted December of 2023, so it's already more than a year. But we have been building a lot of things based on this version of the work. Starting from the parking scenario, the human passenger, in this case, he's no longer driver, telling the system very implicit, right? You don't have to say, let's park at that parking lot near that tree, 50 meters away from us and things like that. This is a reasoning process of, in this case, GPT-4, and then the vehicle, fully autonomous, trying to find that parking space, which is closest to the football stadium. Because the GPT-4 reason that he doesn't want to be late, right? So let's just park as close as possible. And now provide feedback. So he figured out if you park too close, and it might take him forever to exit, right? Because after the game is finished, hundreds of cars trying to exit. So large language model take that as an input, and the next time, still seeing something similar. And this time, the driver is in a hurry to catch the game, but based on the previous feedback, they also want to leave early, faster. So I should park near the exit this time. So this time, the large language model tell actually the planning module to find the parking lot that's closest to the exit. And you can still provide feedback to the system. And that showcase is more like a convenience feature for parking to help you find the parking lot based on the large language model. The second case, unprotected left turn. It's kind of an urgent scenario. And let's see how it reasons. The driver is in an emergency situation, so I need to go as fast as possible while ensuring safety. And you can also see the time delays. This is the background in the console window, how long it takes for the system to work. So the vehicle decides, or GPT-4 decided to turn left before the other vehicle passed. And this, of course, still guarantees the time to collision risk and everything. It keeps tracking all that. But he was not happy about it. Provide this feedback to large language model, and then next time, run into a similar issue, a scenario. But this time, GPT-4 made the different scenario, right? Different decision. The driver is in a hurry, but also concerned about safety. We need to speed up, but also wait for the opposite vehicle to pass. So this time, it decided to decelerate, stop right there, wait for the other vehicle to pass. And this is the bird eye view of the LiDAR sensor. So you can see the vehicle is passing from the other side. You can still provide command on the fly, and then the reason, okay, let's check the perception sensor, check it's clear, then turn left. So there are one iteration, two iteration of the communication, from the vehicle to the cloud. Yeah, he can provide feedback. Okay, I'm good with it. So this time, large language model help address the safety issue by the interaction between the vehicle and the passenger. That vehicle right there doing zigzag, a little bit anomaly, saying something similar, right? Simple. You don't have to describe all the thing. It's just say, that guy is weird, that guy's strange, that guy's drunk, or something like that. GPT-4 decided to turn lane to the right and decelerate. So like, looks like he was a more aggressive passenger. He doesn't like to be decelerated, and just provide the feedback. And next time, smooth and safe overtake. Yeah, we run into those kind of drivers every day, right? So GPT-4 work with the planning module, pick out a overtake trajectory, overtake the vehicle, safe and smooth. But just look at those numbers. Probably you have seen that, probably you haven't paid attention to that, but those numbers are pretty huge. The delays are huge. And we thought it's probably not really realistic to deploy this for real-time scenarios. And even for that, if you take like more than 5 seconds to provide a feedback for the system, that's too late, right? It's not really useful. But before that, I want to show some of the results. We have tested different levels of directness of the command. Some command are somewhat more direct. Some are more, just like more like a hinting. I feel a bit motion sick right now, or I'm going to be late for my work. Some are more direct. Can I drive faster? Things like that. We test all of them, and in turn, of course, large language models can work in most cases, in almost all cases, compared to the traditional systems. The traditional system is we use a keyword switching system. So if anytime it detects a word like faster, then we'll just make the vehicle faster. But it's not working very well, right? The baseline is not working as well as our large language models. And we don't have to go through all these numbers, but basically, the large language model can satisfy the safety metrics, where we use those as the metrics, comfort metrics, where we use some of them, and the time efficiency is not ideal. The LLM latency itself is more than 1.5 seconds, not to mention the communication latency, not to mention the the audio to text conversion latency, which is significant. But overall, our driving score, combining all those different metrics, can be improved compared to a baseline, which is more like a keyword switching system. And it provides all those experience for humans. And of course, we'll also test out a key evaluation that we test out is the so-called takeover rate, right? It's like you drive a Tesla. If you're not happy about something, you take over from the system. We do the same thing for this vehicle, for this system, and we compare that, first, our system compared to the baseline, the takeover rate is significantly less. For instance, when you drive for 10 miles for existing system, you take over probably 10 times, but with our system, you only have to take over 2 times. Things like that. So that's a huge improvement. And also with memory module and without memory module, when you provide feedback to the system knows more about your preference, and you will need to take over less for sure, because you have more interaction. It models your behavior, models your preference a little bit better. But as I said, limitations. There are a huge delay. If we consider the latency of communication, if we consider the latency of the audio to text conversion and also the latency of LLM itself, sometimes it takes 3 to 4 seconds. And again, we use this as the OpenAI's API on the cloud. So it has to be sent to the cloud. There's network latency and everything. And there's also text-based memory module. I talk about we always concatenate all those historical interactions, but sometimes if you have hundreds of interactions, then the memory module might not consume all that, right? It's too much information to consume at one time. And also some passengers still complain that the behavior is not good for everyone. Sometimes it's not that natural and everything, and the context might not exactly reflect what's happening around the vehicle. So those are the limitations that from this work. So that's why one of our ongoing work, which we're doing still, is we want to deploy a lighter version of the model. Probably large model, they have billions of parameters. We want, and we think about whether we need all those different parameters, whether we need such a large model. Why don't we have a smaller model that we can allow it to run on board, on the edge? We don't have to use the cloud. We can make everything running on board, and that's actually an approach that our collaborators like. We are still working with Toyota on this project. Of course, they like it more, right? They can do everything on their vehicle. They don't have to rely on Google Cloud or Amazon or Microsoft or any other third party. They can do everything on board. So that's our current project, and very quickly on this framework. In this case, we didn't use GPT-4 anymore. We used the model called Q1. It's a Chinese version of the large language model by Alibaba. And we are going to try out DeepSeek very soon for the sound reasoning process and we also incorporate vision here. So it's actually a vision language model. It's a VLM. It's not just a LM. But the thing here is we use the VLM to help tune the parameters of the control model. The control model here are MPC for lateral control and PID for longitudinal control of the vehicle. And we also use RAG, base memory module, retrieval-augmented generation for personalization motion control. We have some preliminary research results on this, which I won't go through, but basically, this model, the parameters is just 10% compared to the previous one. So it's much smaller, much more lightweighted. And we don't use as much time as to train it and to fine tune it. We took 4 A100 and then took 5 hours to have one iteration of the fine tuning. And we also collected a lot of data to keep fine tuning the model, not just the public data, but also our own data set to fine tune the model. Yeah, we have some preliminary results, but which basically showcasing that it's a light model, it's on board, but it can still achieve a comparable results compared to the previous version of it. So it doesn't necessarily to have a very heavy cloud-based system anymore, but we can run it on board, and especially as I keep talking about this, the announcement of DeepSeek and their features showcase you don't have to have such a big model with a lot of computational powers, but you can still achieve a very outstanding performance. Here we use a driving score to test that. And yeah, so onboard is something that we are looking at right now, trying to push this to the next stage. But all those other work showcasing how large models, foundation models, can help our autonomous vehicle to better understand the needs from the human passengers or drivers, and then better serve them, right? For safety purpose, for mobility purpose, for sustainability purpose. This is some other outreach slides that I will play at the last. So that's a football stadium. So that that microphone on the vehicle is actually the one that we use to collect the audio information, and we actually run into a lot of hardware things that challenges that I haven't included in this talk. How to collect the words just from the passenger or the driver, but not from the other people. How do we distinguish that? How do we make out, have some filter out all those noises in the cabin? And then a lot of things like that. And we ran through a lot of things. We configured a lot of things and to make that work. And as that they mentioned at last, we're trying to make this faster, to make it more realistic, to be deployed on the real world vehicle. So it has been, some work that we have been doing. Lastly, I want to thank our students who contribute to this work. Just for the record, this student was not hit by a large language model. He was injured by playing soccer, but he was actually the passenger, as you can see from the previous video. This is not my student. For those of you who know, it's Jeff Dean, the chief scientist of Google, who happened to visit us and rode on our vehicle. And one question that I cannot answer him is, why don't you use Gemini? He's the people who have Google's Gemini available, right? He's pretty much the person. But we did benchmark Gemini. We tested all those other systems. It happened to be GPT-4 works better than Gemini at that time. But we are looking to different models and trying to make it work and make our system to behave better. Lastly, I want to thank our sponsor for this research, Toyota, Bosch, USDOT, CCAT, and as well as AutoWare. But thank you very much, and happy to take any questions.
For the really interesting presentation. I'm just coming from more of like how I drive it, so it's an anecdotal question. So if something is urgent for me and the car is not, I would like to take the control of the car rather than giving a command and expecting the car to make a decision. So how do we incorporate the human psychology? Will it affect a lot in the systems, or shouldn't that be a significant factor in when car is making these decisions?
So you are saying that instead of asking large language models to make decisions, you want to just take over?
Exactly. I want to be football game, and because I know already my sister, my brain knows what I want. So all I need to do is I take control of the car.
Yeah.
Why should I rely on?
But think about you are riding a autonomous shuttle, a Waymo vehicle or Zoox vehicle. There's no steering wheel. There's no paddle. There's no way for you to take over at all. The only way that you can interact with the system is just saying words or touching the touch screen to change the settings. So there's no way for you to. So that's the real the story. In our experiment, the driver didn't. The takeover, we mean takeover here. We assume it's a level 4 vehicle. The only takeover is he just pressed the button to deactivate the whole system. It's like autonomous shuttle in the future. You will have that emergency button, right? Press it, it will pull over. That's it. But there's no way for you to drive anymore. So that's the background story. Yeah.
Question and a suggestion maybe. So when you have this translated into command,
yep.
I assume there's only a certain set of parameters you can adjust for the planner, right? So how many cases did you have?
Yeah, great question. It varies by different scenarios, by different application. But for instance, the parking scenario, the trick that we play for the demo purpose is we pre-recorded like 10 different trajectories for 10 different parking lots. And what large language model did is just pick one out of those 10 based on the preference, things like that. For the overtake scenario, we pre-recorded, not pre-recorded, but we have a set of parameters for the vehicle to change lane, to change speed. It's a pure pursuit algorithm that we ran. So what large language model needs to do is just to pick a value out of that range. So there's always a preset range or candidates that the large language model will make decision on.
Like a sort of a suggestion, this is me thinking out loud, is one of the things that, like, as someone who's using the car, like Tesla Full Self-Driving, and it has 3 modes. You put it on chill mode, and like, you don't really know what that means, right?
Yeah.
That does some stuff that's different from like a normal mode. But one thing that can be really interesting doing this is to provide feedback to whatever command I'm giving.
Yep.
I'm saying, like, the car in front of me is driving crazy, take over. And then if the car can tell me that, okay, here's what I'm doing to respond to you, I can actually get a feedback. Okay, the car actually did understand what I'm doing, rather than just me waiting for it to happen. And one very weird question: did the car driving crazy in front of you had any impact on the planner, or no? Or it was just because it was doing this? Does it matter if
it matters? It matters a bit, because if that driver, if he was out of his lane, then the planner will have to adjust, to go probably a little bit further on the left. So it's affecting a little bit on our decisions. Yeah.
I just want to say, starting off, that I definitely relate to the whole turning off those driving, like lane keep assist or the adaptive cruise control, especially on highway situations. And the whole personalization thing, I think, is very interesting until liability enters the conversation, at least on a highway. Because if I'm personalizing to my driving style, which, okay, not all of us have amazing driving styles, I'm not saying mine's terrible, but everyone's doing that.
Yep.
And I noticed that you had the part where you told the vehicle safety. What is safety? So don't you need like some sort of, let's call it firewall?
Yep.
To tell the vehicle, hey, I can't do that.
Yep.
Or for the vehicle to say, hey, I can't do that.
And two things, and one thing I touched a little bit on at the beginning. There is a fallback logic that we can always kick out the system, the large language model-based system, anytime that we figured out the output of the system falls out of a certain, as you said, firewall, a certain boundary. So that's one thing. There's always a fail-safe logic, fail-back logic. You can consider this large language model is a parallel system that's running, but we can always kick it out, fall back to our existing AV stack. And second part, answer to your question is, what if this person deliberately saying something like, let's drive 200 miles per hour, right? Things like that. We also cap that, right? There's always this boundary, say, that's a context information that we have earlier. The speed limit is like this. If you say something upper than that, we bound it. Or if you say something like, let's park on the opposite side of the street, and if the surrounding information, the context information doesn't allow that to happen, large language model will reason to find the closest option to satisfy your needs. So it's not like satisfy all your needs, but we'll try to satisfy as best as possible. Yeah, if that answer your question. Yeah.
Hi, Professor. That was a great presentation. I was fascinated by your words, but I was more interested in the parking scenario. Like the video that you showed, the lot was empty, but what if there was a competition for the spot? Is that something in the scope of your work? Or is that something?
That might be too hard for us. That's out of scope for now. And one of the reasons why it's empty, because that's easy for us to do the research, to show the demo. If there's competition, yeah, that might involve real-time reasoning from the large language model. And in this case, apparently, the large language model on the cloud will not be working. That's why we want to have an onboard system which can provide faster response to say, hey, there is another vehicle trying to compete with us, using the vision model, because we have vision language model, right, to help to make the decision. So that can be something to work on next, but that was out of the scope of this demo.
Hi, Professor. Thanks for your presentation. My question is, how much data is available during the extreme weather conditions? Because as such cases, the data cannot be maybe unavailable.
Yep.
So maybe you will have to rely on the camera, right?
Correct.
So I just want to know how to make this control when and how to resolve this issue?
Yeah, that's actually something that we're addressing right now. Our ongoing CCAP project, where we're looking into extreme weather, whether our vision language model can help to our vehicle to reason, or that during the extreme weather to say, hey, whether it's safe to drive or now it's not safe to drive, what's the confidence of your driving experience. But in terms of data, we did collect some data, but I don't think it's good enough to train a model. It's good for fine-tune a model. We have some hours of recording, tens of hours, if you will, but to have a training from scratch model, that requires a huge amount of data. So that's, if you only have your own data, it's not good enough. You have to have some other source of data to train a model. So that's the answer to your question. Yeah.
Thank you again for the presentation. And I have a general doubt about the slide in which you were explaining that you would aim maybe an LLM agent to write code on the fly, incorporate it to the main stack. So would the idea be that the code that is being updated in the main stack is shared by all the users, or is just used to improve the user experience?
I think the latter one. The latter one. It's just to share to improve the user experience. We haven't thought about the first approach so far, and a lot of times we set a lot of constraints on the code and also the output of the large language model. So the one you talk about for the first part, that's falling outside of our research focus. As I said, everything is more like application driven, how we can leverage this tool to better serve for those different scenarios and make it more personalized. So that was pretty much the focus, if that makes sense. Yeah.
Thank you.
Okay, everyone please join me in thanking Professor Wang.
Thank you.